So we have an acid solution with pH equal to 6, and if it is diluted to 100 times, then the resulting pH is being asked. Now let's assume that the acid is HX, and we have been given that the pH of this particular solution is 6, and I'll assume that the volume of the corresponding solution is some V liter. Now when I am taking the concentration of H plus from here, as we know pH is equal to negative logarithm of concentration, we will be getting the concentration of H plus in the first case to be 10 to the power minus 6 molar, with volume of solution being V liter. Therefore, the number of moles of H plus that are present in the solution, which is equal to molarity into volume in liter, will turn out to be 10 to the power minus 6 into V. Now when I am diluting the solution, what I mean to say that when I am adding water, that means we are making the total volume of the solution as per this question is 100 into V, but as we know the fact that the number of moles are going to remain the constant. So therefore the new concentration of H plus after the dilution is equal to total number of moles upon the total volume, so turning out to be 10 to the power minus 8 molar. And we know any acid, if you take any acid, if its concentration is less than or equal to 10 power minus 6 molar, then in that case we have to consider the dissociation of H2O also. Therefore the pH of the solution will turn out to be less than 7 but not equal to 8. So therefore it will be less than 7, at the same time it will be close to 7. The right answer for this question will be option A, that is 6.95. Now which of the following solution will have the pH is equal to 1? We have various options here where HCl is reacting with NaOH in different circumstances. Now when you write the reaction between the two to form NaCl and H2O, as we know that when the substances are mixed with each other, we will be getting the resultant moles, and accordingly we will be calculating the resultant concentration. So therefore we are given in the option A that we have taken 0.1 into 100, that is 10 millimole of HCl. Option B is 0.1 into 100 of NaOH, that is 10 millimole of NaOH. In option A we can see these two are completely consumed, so therefore there is no question of what you call any residual HCl or NaOH, hence the pH of the solution will remain at 7, that means completely neutral. When it comes to the option B, we can see here that 55 milliliter of 0.1 molar HCl, that is 5.5, 55 into 0.1 millimole of HCl, and 45 ml of 0.1 normal, I mean 4.5 millimole of what you call the NaOH is being taken. Of the reaction between the two, this is nothing but the limiting reagent because it is taken in lesser amount. So here when 4.5 mole of NaOH is being taken, for every 1 mole we are treating with 1 mole of HCl. For every 4.5 goes off, and we will be getting 1 millimole of HCl remaining. So therefore concentration of H plus here is number of millimoles that are finally remaining upon the total volume of the solution. Option B clearly indicate that we have taken 55 ml of HCl and 45 ml of this thing, that means 100 ml we have taken. So this is the concentration. Hence when I find out the pH by applying negative logarithm of concentration, I will be getting it as 2 but not 1. So when it comes to the option C, we have 0.1 into 10 ml, I am going to say 1 millimole of HCl, and 0.1 into 90, that is 9 millimole of NaOH. Hence this is remaining, I am going to say the NaOH is remaining. Obviously the pH of the solution will be greater than 7. So let us rule out this option that it won't be what you call close to 1, because if it has to be close to 1, it has to be essentially an acid. Now here you can see that base is remaining, so it cannot be close to 1. Now coming on to the option D, we have 0.2 molar 75 ml of HCl and 0.2 molar 25 ml of NaOH reacted. We obviously know that this is the limiting reagent of the reaction. So here the remaining amount is 0.2 into 50, because 75 from 75 25 have reacted, 50 are remaining. Now these are the number of millimoles that are remaining. When it comes to the concentration upon 100 is turning out to be 1 by 10. So when I am doing it to find the pH, to substitute this value is turning out to be 1. Hence the right answer for this question is option D. The correct order of increasing concentration of H3O plus in the following aqueous solutions is asked. So, we have various solutions like H2S, we have H2SO4, we have NaCl and NaNO2. Now, the concentration of H3O plus is asked. So, we know that H2SO4, which we have taken as 0.01 molar, is going to produce for every 1 mole of H2SO4 there are 2 moles of H plus ions. Hence, I can expect here the formation of the number of moles of H plus as 0.02. Now, we have H2S which is again taken as 0.01 molar. We know that it is being a weak acid, we will be getting only 0.01 times of alpha. Alpha is the degree of dissociation. So, here we won't be getting what you call the total amount of H2S to be dissociated, as we are aware of the fact that H2SO4 is a stronger acid compared to H2S. Hence, the concentration of H plus obtained from H2S is little lesser. So, when it comes to what you call this NaNO2, we know that the pH of this solution is going to remain at what you call 7 because it is completely neutral. When it comes to this NO2 minus, it will be slightly basic, as we know that this is going to undergo hydrolysis to produce the OH minus, hence the pH will be greater than 7. I mean to say the concentration of OH minus will be more or concentration of H plus is less. So, therefore, the right option for this question is that the acid that produces the maximum amount of H plus ions is H2SO4 followed by H2S, then comes your NaCl, and we have finally NaNO2, which will yield more of the OH minus ions than the H plus. So, the right answer for this question is option C. When 1 ml of dilute HCl is added to 100 ml of a buffer solution of pH equal to 4, the pH of the solution will be, I mean, if you have a buffer, whether it is acidic or basic, if you have got an acidic buffer, you have these reactions taking place, because we know that acidic buffer is a mixture of the aqueous solution of weak acid and salt with a strong base. Now, this being an acidic buffer, when I am adding the HCl to it, I mean to say H plus to it, the acetate ion which are present in excess in the solution because of the addition of the sodium acetate are going to push this in the backward direction to nullify any change. So, therefore, the buffer has a significance that do not change its pH when small amount of acid or base is added. So, therefore, we can say that the correct answer for this question is option B, saying that there won't be any change in pH. Which of the following solutions when mixed will give a solution with a pH greater than 7? Now, we have options like 0.1 molar HCl is mixed with 0.2 molar NaCl. Then we have 0.2 molar 100 ml of H2SO4 reacting with 0.3 molar 100 ml NaOH. Then we have the next option 0.1 molar 100 ml CH3COOH reacting with 0.1 molar 100 ml KOH, and as a part of option B we have HNO3 0.1 molar and 25 ml is combining with 0.1 molar 25 ml ammonia. So, here we know that in this case the pH we want to be greater than 7. Obviously, here when salt is added the HCl, this pH will be mainly due to the acid and the concentration of H plus ion is 0.1, hence the pH of the solution will be 1 but not greater than 7. Coming on to option B, when we have the millimole of H2SO4, you can see that for every 0.2 mole we will be getting 0.4 into 100, that is 40 millimole of H2SO4. You can see molarity when multiplied with the volume in milliliter, we will be getting the millimoles of H2SO4. 1 mole of H2SO4 gives 2 mole of H plus, hence the millimole of H plus which are being used are 40 here, and that of OH minus which are being used 30. That means the residual agent is H2SO4. That means when H2SO4 is remaining, then obviously the pH of the solution is going to be less than 7. Now in the third case, we have these two reacting with each other. When these two completely react with each other, you can see here that for every 10 millimole we have 10 millimole of KOH. That means these two are completely reacting to give you 10 millimole of this salt, and we know the fact that this salt being basic in nature, because we know the acetate ion are the conjugate base of the weak acid, hence it is being the stronger one is going to react with water to produce CH3COOH and OH minus. As we know that these OH minus ions produce, the pH is going to be obviously greater than 7. Now verifying this last option, we can see here 2.5 millimole of HNO3 and 2.5 millimole of ammonia are reacting to give you ammonium, which is again the conjugate acid of ammonia, which is a weak base, hence this is a strong acid, is going to react with water again, but this time when it reacts with water, you are going to get H plus ions with pH less than 7. So the only option which is matching to the question is option C, whose pH is greater than 7. Here the question is, the precipitate of calcium fluoride with a certain KSP is obtained when equal volumes of the following are mixed. When we have the dissociation of calcium fluoride, we are going to form the ions, and we know that precipitation criteria is that the ionic product should be greater than that of solubility product. Now taking the options, the ionic product of this is concentration of Ca plus 2 into concentration of F minus whole square, and the KSP, the solubility product, is given as 1.7 into 10 to the power minus 10 mole per liter whole cube. So here we have the various options which we need to substitute. I mean option A, 10 to the power minus 4 into 10 to the power minus 4 whole square, that is 10 to the power minus 12. This is less than the value. Option B, we have 10 to the power minus 2 of calcium ion with the 10 to the power minus 3 molar F minus. So this is turning out to be 10 to the power minus 8, which is greater than the value. Third option is 10 to the power minus 5 molar of calcium and 10 to the power minus 3 molar of this thing, 10 to the power minus 11, less than the value. I mean to say KSP. The last option is 10 to the power minus 10 molar of calcium and 10 to the power minus 5 molar of fluoride ion is 10 to the power minus 20, which is obviously less than the KSP value. So you can see here the only option that is mapping that the ionic product is greater than that of the solubility product is option B. Hence the correct answer for this question is option B. Now when equal volumes of the following solution are mixed, the precipitation of AgCl will occur only with, I mean to say, once again the similar question is being asked. AgCl, we have a solid with the dissociation like this. So the solubility product is concentration of Ag plus into concentration of Cl minus. So when this value exceeds, I mean to say when this ionic product exceeds over the solubility product, we can anticipate the same. So you can see in option, I mean to say the KSP value is 1.8 into 10 to the power minus 10. In option A, we have 10 to the power minus 4 molar of silver ion and 10 to the power minus 4 molar of the chloride ion, that is 10 to the power minus 8 molar. So therefore this is the right answer for the question. The solubility products of aluminum hydroxide and zinc hydroxide are given. if equal moles of aluminum and Zn plus 2 are present in a solution, which one of the following will be precipitated first? So we have two insoluble salts to be spoken about, and when I consider their dissociation, it's going to happen this way. Now the question is, which will be precipitated when you are adding ammonium hydroxide? Now let me find out the concentration of OH minus which is required for the precipitation of aluminum hydroxide. So the minimum amount of the OH minus that need to be added to carry out the precipitation of aluminum hydroxide is Ksp of aluminum hydroxide upon concentration of Al plus 3 whole to the power 1 by 3. When it comes to the other substance, we have here, it is zinc hydroxide solid, so when we write the Ksp of zinc hydroxide, so therefore we say that the concentration of OH minus which is required for the precipitation minimum of zinc hydroxide is Ksp of zinc hydroxide upon concentration of Zn plus 2 whole to the power 1 by 2. So now it is also given that the concentration of Al plus 3 and Zn plus 2 are same. So when I substitute here the Ksp value given as 8.5 into 10 to the power minus 23 upon, let's assume that the concentration of Al plus 3 which is present in the solution is some x, and now we have the Ksp of this zinc hydroxide as well, 1.8 into 10 to the power minus 4. Now you just check where the concentration of hydroxide and added is less. When you simplify this, you will be getting that the concentration of this OH minus ions which are added for the precipitation of aluminum hydroxide are somewhere around 10 to the power minus 7 molar, whereas this is somewhere around 10 to the power minus 2 molar. That means when I am gradually adding the OH minus ions to the solution, I will be reaching initially the lower concentration, from there I will be reaching the higher. So as soon as I add the lower concentration, when the ions are picking up, those OH minus ions are going to be precipitated. So therefore we can say that this is valid when the concentration of OH minus added is low. In that particular case, you can see here the less concentration of OH minus ions are required for the aluminum but not for the zinc. So therefore correct answer for this question is the precipitation of Al plus 3 is going to take place first. That means the aluminum hydroxide, or option A. In which of the following solvents will AgBr have the highest solubility? The AgBr, which is an insoluble salt, yellow precipitate, is going to dissociate into Ag plus and Br minus. Now the options are option A 10 to the power minus 3 molar NAB. I mean to say, when you are adding the bromide ion again from outside, due to common ion effect, this will be pushed in the backward direction, and we know that the solubility is going to decrease. Coming on to option B, we have ammonium hydroxide 10 to the power minus 3 molar is nothing but ammonia. So I can anticipate here, as soon as this ammonia is added, the Ag plus which is present in the solution is a D block element, has a tendency to form a coordinate bond with the ligands like ammonia, will be immediately undergoing the complexation. I mean to say that the concentration of Ag plus is decreased because of the consecutive reaction or the complexation by the ammonia. So when I am decreasing the concentration of Ag plus, I can anticipate here the reaction to move in the forward direction, and the concentration of Ag plus is going to be maintained, or the solubility of AgBr is increased. So right answer for this question should be option B. Now moving on to the other thing, in pure water we have only this dissociation, and in HBr once again this equilibrium will be shifted in the backward. So in order to increase the solubility of AgBr, we have to add a complex setting agent, is nothing but ammonia or cyanide ion or carbon monoxide, whatever, this is going to push the reaction forward by this consecutive equilibrium which is taking place. So the right answer for this question is option B. Among the following hydroxide, the one which has the lowest value of Ksp at ordinary temperature. This question is little textual. We know that the hydroxide ions, because there is a negative charge on the oxygen, is considered to be hard base because of small size, more charge density or charge, has multiple options like beryllium, magnesium, calcium, strontium, barium. So in each case it will be forming what you call the compound. They are nothing but the hydroxides. When it comes to the combination, we can say that the lattice energy of this particular case is more, for the reason that charge by size of these two values of these two species is almost matching because they are of low size and high charge. So we can say that the beryllium hydroxide lattice energy is high, it's a stable compound. So the Ksp of beryllium hydroxide obviously is expected to be lowest. That means it is not willing to undergo any sort of dissociation to produce the ions. Then comes your magnesium hydroxide and barium hydroxide. Barium is bigger in size and this is small, so it can be easily splitted, giving rise to the high value of Ksp. So therefore right answer for this question should be option D, that is beryllium hydroxide has lowest value of the solubility product. Now what is the dissociation constant of ammonium hydroxide at a given temperature of its 0.1 normal solution has pH equal to 11.27. An ionic product of water in this case is not 1 into 10 power minus 14, it is rather 7 into 10 power minus 15. So in this case what you do, you consider the dissociation of ammonium hydroxide. So you have been asked to find the Kb value of it. So when I am writing the Kb value of ammonium hydroxide, I will be writing it as concentration of the products upon concentration of the reactants. Now it is given that the pH of the solution is 11.27. I mean concentration of OH minus ions can be obtained with that, because you can see pH is 11.27. Now the Kw value is 7.1 into 10 to the power minus 15. So let me first find out pKw, that is negative log of Kw, that is negative log of 7.1 into 10 to the power minus 15, that is 15 minus log of 7.1. This is the pKw value what we obtained, but not 14. Then in that case the pOH of this solution is 15, I mean to say pKw minus pH. So this is the pOH value, and you have been given the concentration of this as well. Initial concentration of ammonium hydroxide is 0.1 molar. When the equilibrium is reached, let's say the degree of dissociation is 0.1 into 1 minus alpha, 0.1 alpha and 0.1 alpha. Now you can see the concentration of OH minus from this data is 10 to the power minus of this much is equal to 0.1 into alpha. So what you will be doing here, you have to get the value of alpha. So therefore the Kb for this expression is 0.1 into alpha square upon 1 minus alpha. Even if I neglect alpha compared to 1, to substitute the value of alpha whatever I have obtained here, the answer is going to be 1.76 into 10 to the power minus 5. Otherwise the answer would have been 1.8 into 10 to the power minus 5 if the pKw of the solution is 14. So in all such questions where there is little complexity in the what you call questions or the answers, you have to choose the wisely the right option by looking at the data properly. Here we will be confused little with the pKw. We'll be assuming normally it to be 14 minus something, but you can see here it's given clearly as this much as your pKw. So when you are getting your pOH from the pH, you please be little careful over here. So therefore the correct answer for this question is option C. At 298 Kelvin, the solubility product is given and its solubility is asked. So PbCl2 is a sparingly soluble salt. So let the solubility of the salt equal to S mole per liter. So then I can expect the formation of S, because 1 mole is giving rise to 1 mole and 2S mole of the chloride ion. So therefore when I am writing the Ksp of this equilibrium is equal to concentration of Pb plus 2 concentration of Cl minus whole square, that is S into 2S whole square. So the Ksp is 1 into 10 to the power minus 6 is equal to 4S cube. So therefore S is equal to 1 by 4 into 10 to the power minus 6 whole power 1 by 3. So the correct answer is 6.3 into 10 to the power minus 3, that is option A. A certain weak acid has a dissociation constant 1 into 10 to the power minus 4. Its equilibrium constant with a strong base is asked. Now when I take any weak acid HA, is going to dissociate into H plus and A minus with an equilibrium constant 1 into 10 to the power minus 4. Now I am going to borrow one more expression from here, that is the reverse to the dissociation of water with the equilibrium constant is 1 by Kw, that is 1 into 10 to the power 14. Now when I am adding these two reactions, you can see H plus gets cancelled to give you HA plus OH minus to give A minus and water. So therefore the equilibrium, when it is summed up, the resultant equilibrium constant is going to be K, that is 1 into 10 to the power minus 4 into 1 by Kw, that is 1 into 10 to the power minus 4 into 1 into 10 to the power 14, that is 1 into 10 to the power 10. Hence the correct answer for this question is option C. Water has pKw equal to 13.26 at 50 degrees Celsius. Its pH is asked. So we know the self dissociation of water. When we write Kw for this, we are going to write like this. Now we have been given the pKw as 13.26, so therefore Kw will be 10 to the power minus of 13.26. Now for H2O, which is neutral, we know that the concentration of H plus is equal to concentration of OH minus. So therefore concentration of H3O plus whole square, when I substitute this relationship here, is equal to concentration of OH minus whole square equal to 10 to the minus 13.26, or concentration of H2O plus is equal to square root of 10 to the power minus 13.26, or the pH of this solution is minus log of concentration of H3O plus, that is minus 1 by 2 log 10 to the power minus 13.26, that is 13.26 upon 2. What I mean to say, the correct answer is option C, which is nothing but 6.63.